Martin, it's great to see you again. It's frightening to think that the last time was 10 years ago, 2011.
Indeed. So it's great we're still alive. Yes.
But you and I haven't changed at all. The world has changed.
Right, right, indeed.
And back then we spoke strictly about cosmology and the implications of it as we look to the universe and your great work. And of course, since then you've really bifurcated your enormous contributions, continuing with cosmology and now focusing on existential risk, which has always been important, which you've highlighted, and obviously with the novel coronavirus COVID-19 has taken on some uh, greater visibility in the public. And so we're going
Indeed.
to talk about
We're thought less
areas.
flaky now than we were. Yes.
So we're going to cover both areas. I should say though, in a bit of a plug for Closer to Truth, when we had our conversations in 2007, 2011, Closer to Truth was really a U.S. based a public television program and on 200 more stations and had a very strong impact in the U.S. Had a website, of course, but it was still 95% U.S. But since then, particularly with Closer to Truth YouTube channel, and we're on live with our guests around the world, we've seen the percentage of U.S. drop and drop and drop, which we like. And so the percentage of U.S. now is below 40%, 60% of the rest of the world, I should say, are the second largest country is the UK with about 11%. India is
Right.
about 6%. So we have a worldwide audience. And so it's really great to speak. And I want to begin by focusing on your really critical book, On the Future Prospects for Humanity. It's in 18 languages, which is remarkable, and a US paperback version is just about ready to be released. And so we want to focus on that. You've also kept up your in cosmology, an important article in Scientific American with Mario Livio, how astronomers revolutionize our view of the future. The universe turns out to be much bigger and much weirder than previously thought. So I want to begin by using that as a base and recognizing that you wrote a history of our understanding of the universe, bringing us up to where we are. So anybody wants to read that, they can read in Scientific. What I want to talk to you about now is about the future. I want to get your predictions, put you on the spot.
Yes.
So given the remarkable advances in precision cosmology over the last few decades, what can we forecast or speculate what might happen, what we might discover in the next, I don't know, 20 years, 30 years, by mid-century? How can we begin to think about that?
Well, it's true, as you say, it's amazing what's happened in the last half century or so, from a time when it was debatable whether there was a Big Bang at all. We are now in a position where we can think of cosmic history with a fair degree of precision, right back to the first nanosecond. And within a few percent, we know all the key numbers, the density of atoms, dark matter, etc., in the universe. So we've made huge progress. But of course, many of the mysteries, like why the universe is expanding how it is, why it contains the things it contains, those lie deep in the first nanosecond, when the universe was squeezed far above the conditions we can simulate here on Earth. And so that's a bit more speculative. And of course, what we hope is that ideas on that very, very early but crucial era will firm up. What we really like to do is to know more about the physics that pertained at the so-called inflationary phase, when the universe expanded from microscopic size, we believe, to produce something as large as the present day universe in terms of content. And also, we would like to know whether our Big Bang is the only one. These are the two fundamental questions. And at the moment, we don't know. We might get clues from observation. We might get clues if we have a theory, which we can test in the lab, which gives us clues to what the physics is at high densities. So we don't know, but that's the kind of thing we hope in this area.
Well, certainly to go back to the first nanosecond and where everything was squeezed together,
Yeah.
quantum mechanics become dominant in terms of understanding the universe. The universe today, we don't need quantum mechanics to understand the structure of the universe today, but then it becomes absolutely critical to do. So, does that necessitate having a theory of quantum gravity in order to understand that first nanosecond?
Um, I think it might do. Let me just say that a nanosecond is a time when all the particles are moving around with energies equal to the highest energies we can produce in an accelerator like the one at CERN. And so above that energy, we have no direct empirical data to compare theories with. So it becomes more speculative. But as you say, there are reasons to suspect that there are crucial elements to a theory which do come in at the stage when the universe was 10 to the minus 36 seconds old or thereabouts.
Right.
And
That's
these are the ones we don't. Yeah. And there are lots of ideas. And if you make some assumptions about the physics, you can then calculate what it means for cosmology. And you find, for instance, that if you make some assumptions, you can understand the fluctuations in the universe, which are the seeds of galaxy formation. And you can even perhaps answer the question, was there one Big Bang or would there be many? Because that depends on the physics. But the trouble is that we don't yet know which the correct physics is.
So there are two kinds of questions we're asking. One is in that first nanosecond, what can we understand about this universe? And we
Yes.
need mechanics and cosmic microwave background and looking for variations and how that relates to theory. But it seems like a whole other multiple orders of magnitude of complexity to get to the question, is this the only Big Bang, or was there a prior cyclical kinds of activities? And that gets into multiverse and brain theory, not brains like on my wall, but brain with membranes of dimensions beyond
Yes.
us. Isn't that doesn't that move beyond our experimental capacity?
Not in the way you imply, no, because, for instance, one of the first follow-ups to the early inflation ideas was Andre Linde's idea called eternal inflation, which is 30 years old. And that was a model which naturally gave rise to a whole succession of Big Bangs. So you can put in certain assumptions about the physics at this era, which naturally leads to that. This then does lead to other questions. In particular, the question is, would the other Big Bangs give rise to cosmoses like ours or not? And this does indeed, as you imply, depend on which version of string theory, if any, is correct, because there are some versions of string theory which say that there can be many different variants of empty space, different vacua, as they say. And in those different vacua, the laws of microphysics may be different. So if the string theorists who say there are many different vacua are correct, then you would have the possibility of many, many Big Bangs, and they would cool down governed by different physics from ours. Whereas if the laws are all the same everywhere, then they would be replicas of ours.
We have followed on Closer to Truth for the last 20 years, Andre Linde, Alan Guth, yourself, many others in exploring this. And rather than coming to a greater consensus, I sense in the last several years, a group of distinguished cosmologists are coming out on the other side and saying that that there really is no experimental or observational test, and therefore those speculations are more metaphysical than quantum physical.
Yes.
Do you sense that, or is it just I'm hanging out with the wrong friend?
People are saying that, but I think the point is not metaphysics, it's speculative science. And the science will remain speculative until we have evidence for which particular version of this theory of extreme physics is correct. And we'll only have that sort of evidence if we can understand and calculate on the basis of one of these theories and see what it predicts about our everyday low energy world. If we have a theory which applies to the very early universe, but suppose it also allows us to get the right value for the mass of the electron or something like that, or things, then of course it will gain credibility. And if it's given us the right numbers for things we can test, we will then take seriously what it implies for the early universe. It's a very important point that we don't have to be able to verify all the consequences of the theory. We have to be able to verify enough consequences of the theory to ensure it gains credibility. But having done that, you then take seriously the theory's predictions, even in domains and contexts where you can't directly observe it. To give an example, Einstein's general relativity is pretty well confirmed in many contexts. And for that reason, we believe what it says about the inside of black holes, even though we can't observe them. And so this theory of very early universe cosmology will only stop being speculative if it gets to the stage when the theory which governs the physics at that time has been validated by low energy observations or experiments.
So this is a very significant point, because the argument against that is that the energy levels required to directly assess string theory are billions and billions of times more stronger than we can create, for example, at CERN. So there's no physical possibility, unless you built a collider the size of the galaxy, that people say. I don't know if that's right or not. In order to access that. But what you're saying is that if there are direct implications for our low energy, our so-called real world, the world that we engage in, that can be predicted out of that would give us,
and if there is any good, there have to be, because the whole point of this unified theory is to actually explain why the forces have the strength they do, why the particles we observe have the masses they do. And so the theory is no good unless it does explain the low energy world. But one interesting question is, it could be that there is a theory, maybe one of these 10-dimensional space string theories, which is correct, but it may be that the calculations are so difficult that we can't do them. And here again, I think this is where AI may help, because just as you know that AI thinks billions of times faster than humans do, it can do calculations billions of times faster and learn. So it's certainly conceivable to me that string theory may be correct in some version, but we will never know it's correct except by letting a computer AI work on it, just like the computers that beat the world champion game of Go and protein folding and all that, and see if the computer at the end spews out the right mass for the proton or the right strength of gravity. And then we won't get the aha insight into having discovered something, but we will then know with the aid of the computer doing calculations far faster than our brain can do, that a particular version of string theory does apply to the low energy world. And then, of course, as I said earlier, if it applies to the low energy world, then we would take seriously its predictions about the very early universe, where, as you say, we can't do any direct simulations.
This approach has actually been used in pure mathematics, where if there's any area that you want an absolute proof, it's pure mathematics, but there are certain kinds of questions that pure mathematicians are still open, but by simulating
that's right.
this on a computer, they're able to show with a very high degree, but not the traditional mathematical proof, that the conjecture is probably correct, probably in quotes.
Yes. But I think in the case of physics, if it comes out with answers agree with observations,
Mhm.
then that's enough as validation.
Okay, well, that's right. Can you put some kind of a time frame on this? A very unfair question, but that's
No,
close to the truth.
not at all. I mean, I think the discouraging thing is that some of these subjects, like particle physics, are moving slower and slower. It took 50 years between predicting the Higgs boson and observing it,
Right,
and
right.
I think it would take a long time. I think we learn a lot more about particles, but there's such a big jump between the energies we can observe and this new unified theory that it's going to be very, very hard to have a theory that applies to the very early universe. And incidentally, another issue which I think will be equally hard is to understand the so-called dark energy, the fact that empty space
Yes. Hmm.
exerts a push which makes the universe accelerate.
Mm.
And we don't understand that. And I think most theorists, although they don't have the details, they suspect that we won't understand that until we can understand the texture of space and time on what's called the Planck scale, which is a billion times smaller than an atomic scale. And this is a scale where gravity and quantum theory overlap.
Mm.
It's the scale of a black hole whose quantum wavelength is the same as its radius. And so I think everyone says that if space, instead of just being a uniform substratum, has a structure, then that structure is going to be probably on this tiny scale. But on that tiny scale, it could have a very complicated structure indeed. String theory says that what we think of as a point in our space may be a tightly wrapped origami in 5 extra dimensions. And there are many variants of this. So I think it'll be a very long time before we can understand the so-called dark energy, which of course has important manifestations in the everyday universe.
Mm. Yeah, certainly in terms of the future of the universe, and is there a
Right.
possible big rip that will destroy
Yeah.
us, or,
Mm.
what happens
Yes.
in the future?
Mm. Mm.
Will everything evaporate
Mm.
ultimately and be taken apart? So let me ask my question another way. What would be the time frame where, if this were not able to be ascertained, would we then have to rethink the whole thing? I mean, is it a 50 years, 100 years, a century, a millennium, a million years? I mean, what, in order to understand the almost epistemological boundaries of our sense of physics, what kind of
Mm.
time frame do you think that is that would be that if we didn't achieve it by time, t, we would
Yes.
have to rethink?
Well, I'm not sure we'd have to rethink. We'd have to await some new clinching observation um, or some more powerful computer, because, of course, there's no reason whatever to think that the deepest aspects of reality are comprehensible by the unaided human brain. It's amazing we've got as far as we have. So it could be that there are many key problems. They may be in understanding the brain as well as in understanding the early universe, which may surpass the capabilities of the human brain. So the answer is it could be that however long humans exist in their present form, there may be some problems they'll never be able to understand. And of course, as I said already, even if they can use computers to calculate whether the theory is correct, that's not the same as having a real sort of intuitive insight
Right.
into the theories what we like to have, and that may be forever beyond human brains.
Uh, I have to say that this is what you said in 2007 and 2011. So
Mhm.
that was one of the first times I had heard
Mhm.
that the limitation may not be the size of the collider that we can build, but rather the capacity of our brains as they evolved for other completely different
Mhm.
purposes.
Mhm. Mhm.
That's a rather pessimistic view,
Yeah.
but
Mhm. Mhm.
we're not given the choice of optimism or pessimism. Reality is
Right.
reality.
Yeah. Mhm.
What about black holes? You mentioned black holes. It seems like there has been an acceleration of progress on black holes as kind of a laboratory, a theoretical laboratory of a test case, which has the energy levels and densities that would apply to the early universe. Are there, as real progress has been made on black holes, are there
Yes.
any implications that
Well,
we can learn?
correct with one thing, they don't involve very high energy densities or anything like that. So they're not at all related to the conditions in the very early universe. But what they are doing are allowing us to test Einstein's theory, as it were, to breaking point under very extreme conditions when it's nowhere near Newton's theory. The most important development in the last 5 years has been the detection of gravitational waves, which is a prediction of Einstein's theory. They've been detected by amazing technology. The equipment needed for that involves a precision equivalent to the width of a hair at the distance of Alpha Centauri. Really spectacular precision. Ray Weiss was a real genius who invented that. This has detected gravitational waves, but more important, the phenomena that it detects are mergers of pairs of black holes orbiting around each other. And from studying the sort of waveform during the phenomenon, you can check whether it fits with the predictions of what you expect, because we can now do computations of how a black hole behaves in curved space. This has been only possible for the last 15 years or so, and we can therefore calculate the sort of template of the oscillations during the merger and the ring down afterwards. And this fits spectacularly with Einstein's theory. So Einstein's theory has survived a much stricter test than ever before. But also what this set of observations is doing is discovering lots of black holes, which are conventionally thought to be the remnants of massive stars. They're finding black holes whose masses are between 10 and 50 solar masses, most of them. There are big debates about how they form. Do they form from binary stars or separate stars that find themselves together for some different reason later, and all that, and are they spinning or not? So this has opened up a new field in astrophysics to understand how these black holes form. But that's a very exciting development in relativity. It's showing that Einstein's theory works in a context where it couldn't be checked at all before. And also the other thing that's happened is that it's been possible to make sharper observations of the very big black holes in the centers of galaxies. I should mention that there are two categories of black holes which astrophysically we expect to exist. There are some which are the remnants of big stars, but there's a separate kind which lurk in the centers of galaxies, which weigh millions or even billions of times as much as a star. And these are now found in most galaxies. They're one of my special interests, and they give rise to what's called the quasar phenomenon. They produce huge jets that squirt out and give you radio emission and all that. And we're now able to observe these close up. There's something called the Event Horizon Telescope, which has got the sharpest resolution so far. And by looking at X-ray observations from gas swirling down, we're learning some more. So there have been empirical advances in our understanding of black holes, which they all vindicate Einstein's theory, but they allow us to discriminate among different kinds of black holes. Ones are how fast they're spinning and things like that. So that's an exciting development in astrophysics. And of course, it doesn't help us with quantum gravity, because that only happens when you get a curvature of space on a microscopic scale. Whereas here, the curvature of space is on a scale of 10 or 100 kilometers in these stellar mass black holes.
Just get your comments on a couple of other issues in physics. Then I want to get into existential risk.
Yeah,
Uh,
yeah.
the controversy in the Hubble constant, where people think that the error bars between different observations
Mhm.
may indicate something of more of a problem than just error correction. What's your
Yes,
sense of
yes.
that?
Well, my betting is that it'll be resolved by people realizing the errors are larger than they thought.
Oh, okay.
That's disappointing in a way. It will be more exciting, of course,
Right,
if
right,
this was a signal for something fundamentally new and different. And
right.
of course, there are lots of exciting ideas that people develop, but it's very hard to find an idea that works. So I think my betting, supported by my colleague George Statue, who I regard as one of the real gurus in this subject, is that the errors in the astronomy and measuring the brightness of the stars, etc., are probably going to be a bit larger than are thought. And
Okay,
so my betting is that the gaps will converge.
good. On the multiverse, which you have
Yeah.
were one of the pioneers on in the
Mhm.
original thinking about how that would work. Over the now 15 years and 10 years since we've spoken together, is your confidence in that reality, how has that moved one way or the other?
Well, as I say, I've never had any confidence in it particularly, but what
Level.
I have said is that it's not a crazy metaphysics. It's a serious scientific speculation, and it's a consequence of some well-defined theories, like, for instance, Andre Linde's theory, but also many others. And so we would like to know, and we will only really know when we do have this theory, which allows us to study the physics back at the time when these big bangs would have popped off if they exist. To be honest, I don't think there's been a huge amount of change in
Uh-huh.
the general ideas in the last 10 years or so. We still are not really much nearer. We've got more constraints on the theory that applies because what we do have are much more precise measurements of the microwave background fluctuations. The microwave background is uh, almost uniform over the sky. It's the relic of the hot, dense beginnings of the universe, but it varies from place to place. And some places are slightly over dense, some slightly under dense, some slightly hotter than average, some slightly cooler than average. And it's from those fluctuations that, as the contrast grows during the expansion, the first galaxies form. So they're very important. But the actual details of these fluctuations are a clue. And in
Mm.
fact, you may remember there was a false alarm when
Yes,
people they
right.
tested.
ISAP too.
They'd found so-called tensor modes, which meant fluctuations of gravitational waves rather than just density fluctuations. And a detection of that kind would certainly narrow down the range of possibilities for the
Mm,
physics
mm.
of the early universe. And people are now using more sensitive instruments on the ground mainly to look for evidence of this polarization, which would be a very important clue.
Well, we need time to discover these things in terms of the reality. We don't know if that's the decades or millennia, but we need time. So that's the perfect a segue to get into existential risk, because
Yeah,
you have now pioneered the frightening prospect that we may not have as much time as we would like to think. Your book on the future prospects
right.
for humanity, as I've said, is coming out in the U.S.
Mhm.
paperback soon, and is really a critical book. And the new version will have a section on pandemics with COVID-19 being added to it. So your book is both prophetic and descriptive. Um,
Yeah.
so let's begin by articulating, enumerating and articulating the different categories of concepts that could constitute existential risk. We have a lot of problems in the world, but they're not
Yeah.
existential. So what are the
Mhm.
categories of existential risk? And I would ask you then, as you list the categories, can we put some kind of odds? That's very difficult, but you've risen to that challenge by putting some kind of odds. We can argue with you, what the odds are, but to put some numbers on the table gives us a benchmark.
Yes, yes. Well, first, I mean, I think existential is a rather fuzzy word. It's used in all kinds of contexts now, isn't it?
Right.
And I would talk about a massive global setback to civilization. It's very hard to think of things that will wipe out every human being, but it is all too easy to think of things which could be massive global disruption to the progress of our society.
Mm-hmm.
And I think we would regard those as existential for civilization, even if not existential for the species. And if we think of events that could be a real setback for our global civilization, there are really two categories. There are the class of risks which stem from humanity's ever heavier collective footprint on the planet. There are more of us on the world, 7.8 billion now, still going up, and we are more empowered by technology, using more energy and all that, and we're causing change in the climate, which could be very serious and cross tipping points by the end of a century. And also we are causing perhaps mass extinction and loss of biodiversity if we're not careful. So the Earth's been around for 45 million centuries, but this is the first when one species has the power to determine the planet's future. And loss of biodiversity and climate change that leaves the world far less habitable, those are one class. But there's a separate class, which I think I firstly discussed in a book called The Final Century, nearly 20 years ago now. And that's that we're now in a world where technology is so powerful that it empowers even small groups or even an individual to do something which could cascade and have global consequences. And the obvious examples of this are bio and cyber attacks. We know already that it's possible for a small group to have a cyber attack that causes massive disruption, electricity grid in a region or things of that kind, or breakdown of the internet. And incidentally, think how much worse this last pandemic would have been if the internet did not function properly during it. We'd have missed a lot. So there are the kind of threats that stem from malfunctions in our infrastructure or in some biological disaster, which could be engineered rather than natural. And of course, the work that I and my colleagues are doing in our centre in Cambridge, I think it's got a great deal more attention and credence since COVID-19, because we talked, in fact, I talked in two of my early books about a global pandemic which could cause massive social disruption, etc. But now we've actually had one, and people realize that we are interconnected and we are vulnerable, and that we should have prepared more for that sort of pandemic. In particular, we've learned that we need to perhaps be a lot more resilient, even if that means being less efficient. We shouldn't depend on a single supply chain where one link in the chain stops a large area of manufacturing, and we should perhaps keep spare capacity in our hospitals for an emergency. And of course, we should be prepared to immediately run into whatever's needed to develop the right vaccine. And I think if we look at the present pandemic, some people have estimated that the cost to the world of this pandemic over the next few years may be something like $20 trillion.
Yeah, I've seen that.
Plus millions of lives lost, of course. And in that perspective, it would have been worth paying several $100 billion as a sort of insurance premium in preparedness, especially as no one could have said that it was especially unlikely. Because not only have we had influenza pandemics, but within the last 20 years, there have been the SARS and the MERS pandemics in East Asia. They haven't spread globally, but they could have done. It was lucky they didn't. And so I like Nate Silver's phrase, the unfamiliar is not the same as the improbable. And we should have taken that into account and been more prepared. But anyway, that is just one kind of threat. There are, of course, other possibilities. But my real nightmare is actually engineered pandemics, because 10 years ago, two groups, one in Canada, one in the United States, and one in Holland, showed it was surprisingly easy to make the influenza virus both more virulent and more transmissible. These so-called gain-of-function experiments, they were for a time not supported by the US federal government because they're obviously a dangerous possibility. And the same sort of thing can be done with a coronavirus. Of course, this does lead to the possible risk of bioerror or bioterror. And this could be catastrophic because one can imagine viruses far more lethal, with a far longer latency period while they're asymptomatic than COVID-19. And of course, these could spread globally. And my worry is that the world is vulnerable because unlike nuclear threats, which are, of course, equally catastrophic, it's very hard to regulate or guard against these because you can't build a clandestine nuclear bomb without special purpose facilities, and the International Atomic Energy Agency can monitor these efforts and verify compliance with treaties or regulations. But cyber attacks and bioterrorism can be done by small groups using quite common dual-use facilities. And what gives me nightmares is the realization that even one such event is too many. And can we really ensure that that can be a level of safety that's achievable without real constraints on some combination of privacy, liberty, and security? We have to give up privacy so we're all being watched, so people know we're not doing something like that, for instance. That's a problem. And of course, everyone says, well, we can regulate against this sort of thing, but enforcing regulations globally has been pretty hopeless in the case of the drug laws and the tax laws, and will be equally hard in this context. So I really, really worry about how we can avoid maybe some lone fanatic producing and releasing some sort of bioweapon. And of course, cyber attacks can be now empowered by AI, and they can be more powerful. I mean, what needed a state level attack now can be done with a small group with AI. And so there's an arms race between cyber attackers and cybersecurity people, not clear which side will win. And I quote in my book a document from the US Defense Department saying that a cyber attack on the US electricity grid would merit a nuclear response if they thought it was a state level attack. But that sort of thing may happen due to a small group. And incidentally, another new scare is whether the command and control systems for nuclear weapons are safely unhackable or not. We don't know about that, and that's another danger. So, so I think we're in a dangerous world simply because small groups of people can have so much impact because they're amplified by these new technologies.
Certainly, this is the most frightening area in reality. I'd also like to get your sense of some of the more speculative or exogenous kinds of events. For example, in the cosmic world, what are there any possible predictions you can have about nearby supernovas or a false vacuum spreading throughout the universe, alien invasions? I mean, these are kind of funny or semi-serious speculations, but do you give any credence or numbers for some of those
Well,
ideas?
some we can't assess, but of course, when people know I'm an astronomer, they think I worry about asteroid impacts
Yeah,
because
astro.
we know they do happen. And of course, they are quantifiable. We know what the probability is, because we know enough about the asteroids, how many there are, different sizes, and what their consequence would be. So we can calculate that. It's not zero. It would be worth quite a bit of effort if we can ensure that we can deflect and it get dangerously close. But the important point is that the annual probability of such an event is not getting any higher. It's the same now as it was a million years ago.
Mm-hmm.
Whereas the things I worry about now
Yes,
are those which are getting more probable year by year because of more human activity. And that's true of pandemics and all the other things I mentioned, which stem from modern technology. So the really worrying things are those which are emergent, where the probability is growing year by year, and is already, in my opinion, far larger than the risk of an asteroid impact, which is very low.
What about malevolent AI, where AI takes on its own initiative and decides it doesn't want any humans around anymore? Is that many
Yes.
people take that seriously? Do you?
Well, I mean, I think, of course, without that, I mean, AI can aid malefactors
Yeah.
by
That's a separate issue.
aiding cyber attacks and all that,
Sure,
and
sure.
and you
That's
have
completely
social
separate.
harm. But the idea of the AI with a mind of its own, um,
Runaway.
uh, well, I should say I'm not an expert on this, but I'm slightly skeptical of the hype. I mean, there's a range of opinion from Ray Kurzweil at one end,
Yeah,
who
right.
seems really able to sing it out in 20 years, and Rodney Brooks at the other end, inventor of the Baxter robots, and I think the vacuum cleaner. And he's very skeptical. He says it'll be many decades before we have to worry more about artificial intelligence than about real stupidity. And I'm rather on his side in that context, although I'm mindful of all the ways in which AI is going to help us in many ways in our science, and also disrupt working patterns and everything like that. It's going to have a big effect on the world.
What I'd like to do now, Martin, is we could literally be speaking for many hours. And what I'd like to do is just give you some topics that are on my mind that I'd love to hear your feeling
Yes.
on, and just get your sense in just a couple of minutes each of these topics. I'd really feel bad if we didn't cover some of these other topics. On space exploration, I think you have you told me a book in process about do we need astronauts, physical human beings, or would AI be sufficient and perhaps even better in future explorations? What's your sense?
Yes, yes. Well, I've just finished a book jointly with Don Goldsmith on whether we need astronauts, and I think the point I'd make is that as robots and AI get better, then the case for sending people for doing exploration or for assembling large structures in space is going to get weaker. At the moment, of course, these robots trundling across Mars will miss many things a human geologist would discover, but that may not be true of the kind of machines we can send in 10 years' time, where they have more sophisticated AI. And of course, the cost and risk of sending humans on a long trip is vastly greater than the cost of sending robots. So my view is that the practical case for sending humans is getting less. And I go one stage further and say that if I was an American, I would support your unmanned NASA ventures in space, which are of practical everyday concern and of scientific interest. But I think the manned or the human program should be left to Elon Musk and Jeff Bezos and the like. And the reason for that is that NASA can't take high risks with publicly funded civilians. The shuttle failed twice in 135 launches, less than 2% failure rate. Lots of adventurers are happy to take that sort of risk,
Right.
but it was too much for the American public. So my scenario is that for practical purposes, humans are going to be less useful, and they can't go obviously to the outer solar system, places like that. But I would hope that there will be some adventurers who will be going on high risk voyages, perhaps as far as Mars by the end of a century. So I hope there will be some people on Mars by the end of a century. In fact, Elon Musk has said himself that he would like to die on Mars, but not on impact. And I think he's coming up to 50 now, but in 40 years he might make that. And I think we should cheer on people like that, but they should not be going at taxpayers' expense, and they should be taking higher risks than we can impose. And the risks are indeed very high, obviously, for humans going for a long voyage in space.
In terms of galactic colonization that science fiction writers talk about, and
Yes.
you can imagine if you deal with time frames on the millions of years, assuming human beings survive the existential risks that we talked about before, that you can imagine galactic colonization. But you can much more easily imagine if it's the super AI colonization, so-called von Neumann robots that can be reproduced.
Yes, yes.
You have this exponential effect. But you ask a really critical question, and I want to put it to you with a short answer. Would it matter in terms of the great scheme of humanity's place in the cosmos if the super AI that we would send out would be conscious or not conscious in principle? This is a deep scientific and philosophical argument. We don't have time to discuss it. I love discussing it, but
Yes,
but
yes.
would it matter in terms of the impact if
Well,
it's
I think the answer is yes. But let me start by saying that I think it won't be humans who do this interstellar exploration. It will be post-humans, engineered, and there may be some combination of flesh and blood and machines. We don't know what combination. And incidentally, I think it'll be the descendants of the pioneers on Mars who do this first, because they're away from the regulators. They could have an incentive to modify themselves. So there would be some creatures. But I think, going back to your question, I think it would matter because, and I know I had this response when I wrote an article on this theme. Some people said, wouldn't it be sad if there were no dominant intellectual entities in the universe who could actually appreciate the beauty and wonder of it?
Yeah.
And of course, the fact is that we can. But of course, some people think that even if you have a brain that is a zombie with far more capability than a human, its comprehension, in the sense of appreciation of beauty and wonder, may not be the same as that of a human. And I think it does make a very big difference the way people view this very long-term scenario.
I've looked to a convergence between the question of whether AI can be conscious and the so-called techno-optimists who claim that at some point in the future we can upload our personal consciousness, our first-person consciousness, into non-biological strata, like uploading our brains into computers. And those are deep philosophical questions that I've wrestled with extensively, and you have. But you actually put a nice way, kind of cutting through all the philosophy. I think you said something to the effect that you'd rather end your days in an English churchyard than in a California refrigerator.
Yes, but that was in response to the people who have
Want to freeze your brain.
frozen themselves in liquid nitrogen, awaiting the time when they can have this resurrection to immortality or to being downloaded. And that's, it seems a pretty implausible story, quite apart from the issue about whether they would indeed in electronic form have the same self-awareness which they had as humans, and also other things. I mean, suppose that multiple copies are made of you.
Right.
Which one is you? These are traditional philosophical issues, but they may become practical ethics in some far distant time, if this can ever be done.
What's your gut sense of it?
I think it's pretty unlikely, and I don't think it's something that we should aspire to. So I'm not going to plan to do this myself. I'm happy with being in the churchyard.
Quick question. How do you now respond to the Fermi Paradox, especially now that we think there are 2 trillion galaxies, each with order of magnitude 100 million stars, and we know that there are a large number of planets around most stars, and a few will be in the so-called Goldilocks zone. So you have this huge numbers, far greater than when you and I spoke more than a decade ago, in terms of possible worlds on which evolution can have occurred. So what's your sense of the Fermi Paradox?
Yes. Well, first I say that the discovery of exoplanets is, I think, the most exciting thing going on in astronomy now. It's surging very, very fast. And of course, as you say, there are millions, possibly billions of Earth-like planets orbiting other stars. And we don't know whether life is such a rare fluke, it only started here, or whether it will be out there. We should look for it. We will, in 10 or 20 years, we'll have big enough telescopes to be able to see if there's any kind of biosphere or vegetation on nearby Earth-like planets. And if so, that'd be really, really exciting, obviously, because it'll show that the origin of life wasn't extremely rare. Of course, the emergence of intelligence we don't know, but let me take an example. Let's take the case where there was a twin of our Earth, where evolution proceeded the way it's happened here on Earth, about nearly 4 billion years of Darwinian evolution, and then a technological civilization emerges and lasts for a few millennia, perhaps. And if we look at scenarios for the future, then I think many of us think that post-human evolution, what I would call secular intelligent design, will take over within another millennium or so. And then it will be electronic entities, and they will persist for billions of years more. So this is relevant to the Fermi Paradox and to SETI, because what this means is that if we were to detect something which is manifestly artificial, a transmission or an artifact or something, then it's most unlikely that it's from some other twin of the Earth which is so synchronized that the few thousand years of a flesh and blood civilization coincided on the two of them. Far more likely a billion years behind, in which case there'd be nothing, or a billion years ahead, in which case we would see electronic artifacts of that, which are remote descendants of that civilization. And so I think what SETI should look for is artificial things, but should not expect them to be messages from flesh and blood creatures. And going back to your question, some people would say, well, why haven't we seen evidence for these? And I think, of course, the Fermi Paradox, it is an important fact that we haven't seen manifest evidence. But I would say it doesn't, in my view, raise the odds against lots of extraterrestrial intelligence very high. And the reason is this, that we've evolved by Darwinian evolution, which favors two things: intelligence and aggression. But the post-human evolution, which would be sort of intelligent design, as it were, is going to be controlled, and it's not necessarily going to favor aggression. These entities may be entirely contemplative. They may want to increase their brain power, etc., but they would not be territorial or expansionist necessarily. So I think it's being too anthropocentric to assume that they want to come and conquer us if they're there and all that. They may be out there already, thinking deep thoughts, and not using very much energy and not wanting to explore. So there could be lots there, and we're not of any interest to them, and so that's why they're not here. So I think the absence of evidence is not evidence of absence of even superintelligence.
Right. My problem with that is that this is one of an increasingly a favorite explanation of Fermi, or potential explanation. There are 50, I think there are books that have 50 or more possible explanations, but the problem
Right, yes.
is that every explanation you give, you have to assume that it is inviolate, that covers everything. Because as we talked about earlier, the possibility of our species expanding in the universe, whether through AI, Van Neumann probes, gives the possibility that in what would seem to us a lot of time, tens of millions of years in galactic history, that's a kind of a blip. And so if you allow our expansion over tens of millions of years, assuming we survive existential risk, there should be things that we can see. And the fact that we don't, I think has more significance. And every explanation for Fermi Paradox is a real explanation. The one you gave is an important one. But it has to be ubiquitous. It has to apply to everything. And because even one or two escaping from that should have shown evidence.
Well, it might, but you use the word we. And the point is that our remote descendants who are going to embark on interstellar voyages will be a quite different species.
Right.
They'll be engineered. And so you can't assume they have any of the motives that we had. So I would come back to my point and say that there'll be electronic entities and they may design their successors, etc. But there's no reason to think that they will carry into the far future the sort of motives that we would have.
Okay, but that has to apply to every single case, because if one or two would be different, then so that would
I mean, there could be some, because obviously we've only searched a tiny corner of the galaxy by a limited range of techniques. So we haven't done very much research. I mean, some people say it's like looking at a spoonful of ocean water and saying there's nothing living there. And so we can't be too definite that there's nothing out there like us. But my main point is that future evolution is going to be not on the Darwinian timescale, where it takes 1 million years for a species to change, but on a technological timescale. And that's why even a few centuries from now, the dominant species may be very different from us and may have no real emotional affinity with us today.
Martin, I want to spend some time on a topic that I've been dying to talk to you about for a long time, and that is one of my favorite all-time books was your Just Six Numbers, The Deep Forces That Shape the Universe. I think it was published in 1999, so now more than 20 years. It's a book that catalyzed to many people the so-called fine-tuning problem or fine-tuning issues, which has been used to support a multiverse by many scientists. It obviously has been used by in certain circles to justify supernatural causes or a creator. Some scientists today even deny that there's a fine-tuning problem, that the bandwidths for structure and life are broader than you and others had thought, and that you didn't modify a constant in combination as opposed to individual. So a lot of issues. So I just want to get your reflections back now more than 20 years after you wrote that, and begin by asking, if you wrote that book today, would you select the same numbers? Would you have different ones? Would you add some?
I'd select the same ones, because in fact I was late enough to include lambda, the cosmological constant, because the accelerated universe had just been discovered. And if I'd written a few years earlier, I've missed that out, but I got that in. And honestly, I don't think I would have wanted to change them. I think they are the key ones. You could pick another selection, obviously, but I think I wouldn't want to change that. And the basic arguments, I don't think change very much. As regards the tuning, I think, as you know, if we look at all the things that had to be fulfilled for us to have emerged, then there are lots of very tight tunings. But I think if you ask the more generic question, what are the range of the parameters which allow some kind of emergent complexity, then you don't get such fine tuning. And if we say, what do we need? Let's say we need stars, and I think we would need a periodic table. In fact, I thought quite a bit about a universe of just hydrogen. And you get Fred Hoyle's black cloud with no other kind of intelligence out of that. And so there needs to be something like chemistry in order to have complexity, etc. And that requires constraints on the nuclear forces and all that. As far as gravity is concerned, gravity has to be very weak compared to the microphysical forces in order that large things can be pulled together by gravity without crushing smaller things. But it doesn't have to be fine-tuned. I mean, if gravity was, say, 10 or 100 times weaker, that might be even better, because stars would live longer, planets could be bigger, we could be bigger without being crushed, etc. So there's no fine-tuning, and there's just a range. And that's true for most of the other numbers. So there are constraints, and as you say, if you consider multi-parameter ones, then it becomes more complicated. So there are constraints, but if you just say what's the requirement for generic complexity, that doesn't narrow things down as much as if you put in all the special things that had to be right in order for entities like us to exist. So I don't think, and in fact, I had a paper with Mario Livio on this as a preface to a book on this subject just out last year, where we took this line that the fine tuning is not all that fine if you just say we're trying to explain under what conditions you get generic complexity.
What justification do you see for the fine tuning, as you see it, to give support to a multiverse, which of course comes about for totally different reasons? It's the result of physics, but does the fine tuning, as you see it, give any support to a multiverse?
Well, I mean, it gives, I should say that the reasons for taking multiverse seriously, in my view, are that it's a consequence of many of the most carefully worked out theories of the early universe.
Yes.
The Linday model was the first, but there are many others. So I think the case for the multiverse is independent of fine tuning. But I think if the other universes are governed by different laws, then of course that does mean that there will always be one universe with any degree of fine-tuning you want. And the question is, how surprising is it,
right,
if there's only one universe that it's allowing us to exist? And the answer is it's somewhat surprising. Well, it's very surprising for us to exist, but I think that's not the right question to ask. You should ask, what is the likelihood of some possibly complex entities being able to evolve? And as I say, you need gravity, you need some sort of periodic table, and long-term stability of stars and all that. But that's all.
We can go on forever. I just want to ask you one kind of final observation. You've speculated about not the far future, but the far future, the ultimate future. So if you had to summarize your view of the far future of life and sentience, however you want to define that in the cosmos, what is your best sense now?
Well, of course, there's a very pessimistic view, which is that life is so rare that it only exists here and we might stuff it out. leaving a lifeless cosmos. But I would say that probably there are entities far more complicated than us out there already. And also, I would note that we are nearer the beginning than the end of cosmic evolution, because the sun's been around for 4.5 billion years. It's less than halfway through its life. And the universe has a far longer, even perhaps infinite future ahead of it. And moreover, future evolution beyond humans could be faster because it's on a technological timescale,
Right.
not on a Darwinian timescale. And so my prediction would be that there are entities out there which are so different and so alien to us that we can't maybe even recognize them, can't understand they're there, simply because there may be other planets that form much earlier and where evolution had a head start. But then if you think of the future of our remote progeny, then of course they may turn into entities which may, when they're no longer human and constrained by human requirements and human limited lifespans, could very well spread through the galaxy. Although I would suggest that if they're really, really advanced, there's no particular reason why they would want territory. They might just sit in a virtual world thinking deep thoughts. And maybe they're out there already.
Well, my deep thought for now is that it's really a shame that this is our first conversation in slightly more than a decade, and my commitment, and I hope it's mutual, is that we do it our next a lot sooner than we did between the last and now.
Indeed, I very much hope so. But it's great to be in touch again, and I hope you've been interested in some of the things I've said.
Been interested for a long time and will continue to be, and it's great to see you keep up your enormously important work. We'll follow it, we'll support it, and I look forward to seeing you again very soon.
Good. Thank you very much.